Welcome to today's Explainer. Today we're actually pulling back the curtain on some of the most, absolutely fascinating invisible math in the world. Have you ever just stopped and wondered how your phone always knows exactly where you are, literally down to the meter? Or how engineers manage to talk to spacecraft that are just zooming overhead? Well, it all relies on this one foundational concept that essentially makes modern navigation and really all space technology completely possible. I want you to really think about this for a second. How do you actually map a spinning planet? Try to imagine tracking moving objects, planes, cars, or even just yourself on a surface that is constantly, relentlessly rotating at hundreds of miles per hour. Without a fixed reference point, it is absolute chaos. Everything is just constantly moving. So we really need a way to pin down the math on a world that completely refuses to stand still. Okay, let's dive into this. Here is our roadmap for today. First, the spinning globe problem. Second, introducing ECEF. Third, visualizing the XYZ axes. Fourth, ECEF versus ECI. And finally, from global to local. So, Section 1, the spinning globe problem, and specifically, Earth's rotation. Okay, imagine if we were to use a completely non-rotating coordinate system to map the Earth. The math would get wildly complicated very, very quickly. Think about it. Because the Earth is spinning, if you were standing perfectly still in your own backyard, a non-rotating system would mathematically record you as literally flying through space. Ground stations, massive cities, the GPS receiver right there in your hand, they would all be continuously changing positions in the data. It'd be an absolute nightmare for engineers just trying to calculate a simple distance between 2 points on the ground.
Moving right along to Section 2, introducing ECEF, which is really the ingenious solution here.
Meet ECEF. This is absolutely the hero of our story today. It stands for Earth-Centered, Earth-Fixed. And ECEF is essentially a 3D coordinate system that is quite literally attached to the Earth. The origin, the true 0 point, is located right down at the very center of the Earth. So the crucial takeaway here is that because these axes rotate together with the planet, locations on Earth remain basically fixed within this specific mathematical frame. It centers on the Earth, and it is entirely fixed to the Earth. And guys, the stakes for this are incredibly high. ECF isn't just some abstract textbook theory. It's a crucial system powering almost everything that moves around us. It's the hidden architecture tucked inside global navigation satellite systems, your standard GPS, satellite navigation, space engineering, geodesy, Earth observation, and basically all tracking systems. Literally every single time you open a Maps app, you are silently relying on ECF. All right, Section 3, visualizing the XYZ axes and really understanding this XYZ frame. And this brilliantly illustrates how it all comes together. I want you to mentally build a giant XYZ frame inside a completely transparent Earth. Got it? Now let's place the origin point right down at the Earth's molten core. The x-axis points perfectly out towards 0 degrees latitude and 0 degrees longitude, so that intersects just off the coast of West Africa, right in the Gulf of Guinea. Then the y-axis points out towards 0 degrees latitude and 90 degrees east longitude. And finally, you have the z-axis, pointing straight up toward the North Pole. Now picture the actual mechanics of this internal frame as the Earth turns. The x and y-axes are completely locked into the planet, right? So they rotate and just sweep around as the Earth spins. But the z-axis, the one pointing directly up through the North Pole, that one stays perfectly aligned. It essentially acts as the giant spindle that the whole system is just spinning around. And this completely solves that initial problem we talked about earlier, because this internal 3D frame rotates right along with the Earth. Fixed spots on the Earth's surface stay mathematically fixed. Whether we're talking about a massive ground antenna, the entire city of Sydney, or the UNSW Canberra campus, they all remain at basically the exact same ECEF coordinates day and night, entirely regardless of the planet's constant rotation. It's a total game changer. Let's jump into Section 4, ECEF versus ECI, global versus inertial. Now what's really interesting about this slide is the visual analogy, because it usually creates a massive aha moment. Think of ECCF like you are standing directly on a spinning carousel, holding a coordinate frame in your hands. From your perspective, everything else on the carousel looks completely stationary, right? Well, ECI, on the other hand, stands for Earth-Centered Inertial. Imagine ECI as a camera positioned completely outside that carousel, just watching it spin. From this outer camera's perspective, the objects attached to the Earth are continuously moving. So let's look at this data cleanly contrasted here. ECEF rotates with the Earth, which makes it absolutely perfect for tracking GPS, mapping, and ground stations. ECI, however, does not rotate with the Earth, which makes it perfect for tracking satellite orbit dynamics. Space engineers absolutely have to keep these two very distinct. Basically, you use ECF when you actually care about a specific point on the ground, and you use ECI when you're analyzing a satellite just zipping through the vacuum of space. And finally, Section 5. From global to local, getting into practical navigation. So here's the thing. ECEF operates purely in Cartesian math, meaning simple x, y, and z coordinates. But human beings, we don't navigate using x, y, z. We use maps. So real navigation systems take those internal x, y, z coordinates and they use fundamental conversion math, stuff involving Earth's radius and complex spherical geometry, to translate them into latitude, longitude, and height. And, actually, because the Earth isn't a perfect sphere, it's kind of squashed, real systems use a model called the WGS84 ellipsoid to make sure those conversions are incredibly accurate. Let's move to and see how this builds into an actual data pipeline. When your phone connects to GPS, step 1, it first receives the satellite's position in global ECEF coordinates. Step 2, it calculates your receiver's position, again, also in ECEF. But engineers know ECEF is a global frame. So for you to actually navigate your neighborhood, we move to step 3, converting that data into a local frame like ENU, east-north up, or NED, northeast down. This local interpretation is exactly what makes that little blue dot move so smoothly across the map on your screen. Now, if your head is spinning just a little bit right now, please don't worry. This is notoriously known in space engineering courses as a really tricky math patch. Students frequently struggle with mixing up that spinning ECEF frame with the stationary ECI frame. It's so easy to just forget the Earth's rotation or to confuse a local ENU frame with that massive global ECEF frame. I mean, visualizing 3D axes inside a transparent Earth definitely takes some practice. Just recognizing these hurdles proves how much complex foundational knowledge you've actually absorbed today. So, you now know the secret to tracking a moving target on a spinning globe. But it leaves us with a pretty incredible thought. If every single dot on your GPS relies on this massive, invisible, spinning XYZ frame buried deep inside the planet, what other brilliant, hidden math is silently guiding your everyday life? Thank you so much for exploring this with me today, and I really encourage you to keep questioning the invisible systems all around you.